those tend to be the easiest symmetry operations, at least in my mind, to see. There are other more complex ones. One that can appear to be simple, but actually has multiple ones in it, is a symmetry of rotation. So rotating a system around and ending up at the same point. An example of this, can you hand me that, Joe? Let's pretend the yellow part was not there, but what type of, if I'm looking down this plane, right along that way, what type of symmetry of rotation would I have for this system? The bottom is a square, the sides are a rectangle. Well, oh, actually, they're both rectangles. Okay. Yep, 180 degrees. If it were a square, you're right, it would be a C4. In that case, it'd be a 90-degree rotation. But because these are both on each, well, on every face, it's a rectangle, it's only a C2. Let's talk about that. Or 180 degrees. Rather than saying 180 degrees, we would say C2. It just shortens things up.
Like every 90 degrees
No. Yep, it has to deal with 360.
Right, so the C4 is like 12
No.
We'll get there. It's given the symbol C sub n, where we're going to define n. It's a rotation about an axis. C sub n, what you're doing is it's 360 degrees divided by n. And that is your degree of rotation. So let's say we have a C2, like we just saw. It's 360 divided by what? 2 gets us a value of what? So it would have a 180 degree rotation. What about our C4? It's 360 divided by 4. What's that equal to? 90. So it's a shorthand way to do that. Does that make sense to people? Okay, what was that? Does not, yeah, it takes a little bit to get there. What we're going to do next is we're going to look at a molecular system. Then we're going to consider different symbols drawn to indicate different C sub n axes. Remember when I showed you that space group picture and there was a bunch of just weirdo symbols and it looked like hieroglyphics? This will alleviate some of those hieroglyphics. Okay? Not all of them, but some of them. Actually, probably by the end of this week, you should be able to read most of those hieroglyphics. Okay, example. What is the Cn for the axis centered on the boron in BH3? We're talking about rotating this guy. I'm going to label these hydrogens 1, 2, and 3. Are they actually different though? No, they're not really different. Okay, and the axis we're talking about is looking down the center of that boron. What's our rotation to end up? Do you have a question about this, Joe? Yes, there's many different C's. We'll probably go up to C6. This is a C3. Okay, because what kind of rotation would we need to arrive at a similar structure? Yep, if we rotate by 120 degrees, we end up at that same structure. However, where does H1 move to? Yep, oh, sorry. H1, what's this guy? And this guy. Okay. And what type of axis did you say this was, Joe? A C sub what? Yes. We have a C3 rotation.
Are there like weird like C3 point whatever or
No, these have to be a whole number that's divisible. So that has to be a whole a whole number. When we have other situations, they're other symmetry operations. Like there's one that's a rotation followed by a reflection. It's called a roto-inversion or an improper. We're going to talk about that one next. Yes, so there's nothing like that. A tetrahedral has an improper or a roto-inversion symmetry that's indicated that way. Tetrahedrals, though, do have a bunch of C3s, depending on what axis you look down. So do you want to look at a tetrahedral? Okay. We're not going to go through all the symmetry elements of that tetrahedral because we haven't talked about it yet. Give me a molecule that has tetrahedral symmetry. Okay, methane, perfect. CH4. We're going to draw a 3D representation of this guy. Does everybody feel comfortable, with what this means? Okay. There are many different rotational axes in here. Which ones do you see?
can you label the H's so we can refer to it like that? We can kind of have one.
Yeah, sure. Let's do A, B, C, and D.
There's one looking down from the top.
So yep, there's one looking down directly that way. I'm going to label that one in green. What type of rotational axis is this one? It's a C3. What about along this axis? What about this axis? This axis. Okay. Any other ones?
I want to say there might be a C2, but I feel like I need to hold it. Definitely help.
There is definitely a C2. So let's say we rotate this system where these hydrogens are pointing out at us. The other ones are pointing down in the board. There's a C2 right here. So if I kind of cut that guy in half, C2, there are many other C2s in here. Okay?
The Fisher projection is a C2.
I don't know if that's called the Fisher projection, but that type of projection, yes.
They will be wrong.
Yeah. Okay. We're at the end of time. End of time. It sounds dramatic. We're out of time for the class. Next time, what we're going to do, we're going to draw different symbols associated with C's. So, for example, this indicates a C2. A triangle would be a C3. What do you think a C4? Yeah. And then pentagram for a C5 and a hexagon for C6. Oftentimes, we leave C5 out of the picture, though. Pentagram. It is. Catholic school. No black masses. All right. Again, I will give you access to Avogadro, or excuse me, WebMO, where if you plunk molecules in, you should be able to see those symmetry operations. For you guys, what's more important is being able to have an understanding of what that symmetry operation is and spotting at least one of them in a system. Okay? You do not have to know all of them. Just recognize when you see one, and then eventually, when I get those hieroglyphics back up, you can look at that and tell me what type of operations are happening. Okay?